What do you know? So, any questions on the stuff you just got back? And, talk to me in private if you're, we'll try that, we'll try leaving that open. Cool, so I kind of want to work problems today. I want to wrap up that first section. If you want to read ahead, if you're interested in reading ahead, you could read about infinity, plus or minus infinity. I'm going to take a digression from the book and talk a bit about infinity in here, because this book doesn't really have any of the big infinity stuff in it, and that stuff's so cool that we have to take a day to talk about it, because I think it helps understand R a little bit better, and the rationals and the irrationals, and why there's so much more of one than the other. So maybe read ahead section 5 in that first chapter. And then there's this whole chapter 6, and it's even got an asterisk on it. It says a development of R. I am not going to go through that, but you should read that on your own, and we can talk about it all you want. But I don't feel like you gain anything skill-wise from reading that. It's good information, it's a cool story, a cool math story, but it's all about these things called Dedekind cuts, which are a way of making sense of the real numbers. Check it out, see if you want to talk about it. If you're good and you're like, I don't want to talk about it, cool. Don't worry about it. And then probably the next core thing that you could start reading is chapter 2. Chapter 2 is on sequences, and that's when we're going to start pulling a lot of this sup-inf stuff in. I've got a result today that I want to show you that's not in our book, that I don't know why it's not in our book, because it really helps with a lot of the sequence stuff, but oh good. So that being said, I'll have a little time to think about this. Can I ask, what was the first thing you did when you saw this problem? What was the first thing you did on your paper?
I made 2 example sets.
I like it. That's what I would do too. So what did your picture look like? Can I take a look at what?
I just made S equals 1, 2, 3.
Oh, okay, cool. So do you mind if I write those down? So first thing Cormac did was try to get some intuition by drawing sets. That's what I would recommend. That's what I would do. So what was your S?
1, 2, 3.
And then 4, 5, 6 was
Yep.
the T. And I guess I would also probably draw the real number line out, because that helps me think a lot. So these sets here, so if we had 1, 2, 3, and then 4, 5, 6, that's a good set, but it's not a terribly troublesome set. The troubles always come in infinite sets, so that's an awesome place to start. We've got a finite set here, but I would recommend thinking about cases like this, but then also infinite sets involving intervals, both open and closed. Does that phrase make sense when I say that? Because we didn't talk about it officially. It's got, so open, closed, half open, half-z's, something like that. So the half-z's would be like this. Sets like that. Those are a good place to start looking, for sure, for examples. So let's see. What did anybody else do to start? Something different? Okay. I'll take your word you didn't. But seriously, drawing pictures would be a huge help. So I just take the real number line, I'll sketch off some stuff, make that S, and make this T over here. One's a half Z, one's open. And things can get weirder from there, but we try to start with just what can I get some sense of. Okay, so talking about just strategy on how to approach this. So the key thing is, this condition here is that no matter what S I pick, it is less than or equal to any other T I can pick. So that gives it, that was the first thing, like how do these sit? And this was the key bit of info here, that S is left, and I put in that parentheses because maybe, of T. That might get a little bit more complicated, but it gives us a rough sense. Cool, so what about this first question? Let's start with, why is S bounded above? Liv, did you come up with anything for that?
I guess I just like looked at the definition.
Cool. Yeah, let's look at it. Okay, so let's look at, so a set S is bounded above, and what was that definition?
If S is a subset of the reals and S is non-empty, and then if X is less than or equal to M for all X in S, then M,
Yes.
then M is an upper bound.
And where does this M come from? What is that, where did that M, because it just kind of popped up here, but there's, like, what do we want to say about that M? Where, yeah.
It's an upper bound, right?
It is an upper bound, yes, definitely. So we've got, I'm just thinking, reading the sentence, S is bounded above if, this is awesome stuff, this gets it clear, S is a set of real numbers, subset that is non-empty. But then we just kind of cut to this, and X is less than or equal to M for all S. We didn't say what M was, and we kind of want to toss that in. So how would we introduce M into this statement? And what I'm thinking are these kinds of things we want to practice with those guys, the quantifiers. We've already got the for all in there. How could I make this M appear as part of the sentence? Just part of the sentence.
I guess you could say like, for every M in the reals. I don't know.
Would that be true for every M? So here we got our set S right here, here's S. And it looks like we're saying that if I pick an X out of here, the M has to be to the right of it. So not every M, right? This M wouldn't work. That's not an upper bound.
Mm-hmm.
What I'm just looking for is there exists, that's all. And it's a little more, you're probably thinking much deeper than what I'm asking. So S is bounded above if, and we can find, let's make it in plain language, we can find M, which is a real number, such that. So that's all I was looking for. And maybe that was, you weren't quite sure what I was looking for. Do you see?
Yeah.
Yeah, cool. Just we're practicing getting these quantifiers in sentences and putting them in the right place. Cool, so here's my set S. I've tortured Liv enough. Camila, my friend. How do I know this set S is bounded above?
Because we know there's a T, like that's greater.
Yeah, any of
Or
these
equal
T's.
to.
Yeah, definitely. Yeah, exactly. So because of this relationship, we've got a whole, these are both non-empty. So we know there's something in T that's bigger than every S. And in fact, any T out of this set is an upper bound. Nice, awesome. Are we cool with that? Everybody good? All right, so let's see here. Why is S bounded above? Because any T, how about we say this? Any T in the set T is an upper bound of S. And then, Camille, let's just finish this up. Yeah, what's the next part?
Now we know that T is bounded below because there's an S. That's good.
Beautiful. And so T is bounded below because this is non-empty and there's something in here less than or equal to any of the stuff in there. So we'll just say that. And so this is because any S is a lower bound on T. Now, why do we care about this? Christian, why do we care about that? Why is it important to even talk about step A before we go to step B?
Because you need to prove that set S is bounded above and set T is bounded below in order to show that there is like a supremum or an infimum of either of those sets.
Yes, yeah, exactly. So before we can talk about sup and inf, we have to know it's bounded at all, that there is some bound. So the question here that they didn't ask, but I asked, why does this matter? Because to talk about sup, we need to know there is at least one upper bound. At least there, I shouldn't have probably used that because we're going to find the least upper bound. There is some upper bound. And to talk about inf, similarly, inf, the existence of inf, and I'm going to say it a different way, the existence of an infimum requires a lower bound, some lower bound. Cool. Thank you. Feeling good? Just trying to pull it together, practice our stuff, make sure we get the little important details, because a lot of analysis is about tiny little details. So now let's go to the thing we got to prove. We need to show that the supremum of S is less than or equal to the infimum of T. So prove with the definition of those sets, infimum of S is less than or equal to, sup of S is less than or equal to the inf of T. Cormac, did you get anywhere on that?
Yeah, I said, so the supremum is the least upper bound, and because every element of T is an upper bound of S, the supremum of S is the smallest element of T, I think is how, and then...
So yeah, so that's pretty close, but we don't know that the sup of S is in T, so let's just really quick. So you're definitely on the right track, but what if T looks like this, nice and not even, there's no funkiness, or even in your sets that you gave, we could go to those. We had S, the sup, what was that last thing you said?
So I think I said the supremum of S is the smallest element of T, but it's less than or equal to the smallest element of T.
Yeah.
And then if you just say it the other way around for the infimum of T, I forget, I should have wrote it down.
It's okay, it's all good. And no, it gets hard to talk about. Even I have hard trouble talking about it, just like sporadically. Yeah, so let's try to cobble a proof together. That's basically the heart of it. So we know that well, actually, let's put up the definition of sup again. Let's put those here so we have them right by our side, so we can pull these together. So definitions, and I would write these out. Oh yes, good reminder. Let's have a quiz next Monday. Okay, quiz next Monday. It won't be a long one, but it will be definitions and theorem statements. So I'll probably add a few to this list and just kind of post it on World Class to make sure you have it in the next day or so, but just to make sure. Definition of soup. How about we say upper, lower bounds? And when I say we want the definitions, this is why I was grilling Liv. We want to get those exact wordings in there, right? Like there exists this M that is greater than or equal to all the things. So we want precise wording, and you want to practice that. If you're not sure how to practice that, let me know, and I'll help you. I'll help you figure out a way to do that. Upper and lower bounds, soup, inf, Archimedian Principle, which we'll maybe get to today, I hope so. The denseness of the irrationals in R, and I kind of think that might be about it in terms of definitions. Oh, the completeness axiom. Yeah. And that should be enough. And so I'll just like write these down. You give me the precise statement as in the book. And I'll give you a grade on how close it is to how precise it is. You leave out a quantifier, get a little dink there. So why don't you practice right now? So we have this set S, subset of R. S is non-empty. Let's say M equals soup of S if there's two things. And let's say little m equals inf of S if two things. One of them we talked about already today. against above. Nice. That's good, that's okay. I do love feeling good about it.
So,
Nice, yeah, solid.
do we have to say that?
So, yes, yeah, that's good. So what was your question, I'm sorry?
Do we have to say that? Like, explain that this exists?
Let's see, yeah, that's a good question, so let's see. For all, so for any. Yeah, great question. How's it going, Cecil? Good on it? Nice. Could you help me, Cecil, with the, if I say Cecil, is that bad? Yeah, is that okay? Sorry. I'm just like it's tough, like multiple syllable names, it's just like tough for my brain. I can't get Christian any shorter.
Chris.
Yeah, but you don't want to be called that, do you?
Doesn't really matter to me.
Seriously?
Yeah, if you want to go for it, you're welcome to.
Okay, I can't call you C. I usually like devolve to first letter in the name at some point, but then it's a lot of confusion.
Fair enough.
There's 3 C's. There are 4 C's in the room. I can't, yeah, my God. So, C's. What are the 2 conditions?
If M is an upper bound,
Okay, so M is an upper bound, which automatically tells us that the set S is bounded above. So we're good to go. Yes, and then what else?
and if M prime is less than M, then there exists an X in S such that M prime is less than X.
Yeah. Yeah, exactly. It's a hard thing to get your mind around, for sure. Let's draw the picture and make sure we make sense. So, here's an M that's an upper bound, but it's not the supremum of this picture set anyway, because if I pick this M prime, there's no S, there's no element of the set inside this interval. So it's all about, I am the supremum if no matter how far left I fall, there's stuff in the set between that new left endpoint and what I'm claiming the supremum to be. Does that make sense? So you fall a little to the left, oops, the set's now to your right. That's what that's all about. Awesome, very nice, thank you.
Makes sense.
Yeah, would you do this? Yes, and I was like trying to decide if I was going to say Chris or not. Sorry, that was one of my
no
brain.
worries. So you would kind of just flip things around and say if M is a lower bound, the
Yeah.
first one, and then if M prime is greater than M, then there exists an X within S such that
If M prime, sorry, what was
if
that?
M prime is greater than M,
Yeah.
then there exists an X which is in S such that M prime is greater than X.
Yeah, exactly. Yeah, beautiful. Same thing, right? Here's little m prime. If I pick, this is little m, this is my inf. If I fall a little bit to the right, instantly now there's stuff in the set that's lower than that number. Cool. Feeling better, Cormac?
Yeah.
Okay, awesome, good. We just want to leave here feeling all right. We don't want to leave here feeling stressed about analysis. There's real shit in life to be worried about. We don't want to be stressed about this. Okay, cool. Anybody got a proof idea? This one I'll just like open up here. It's a little simpler than you might think. But I'm curious what you got. Has anybody got anything they want to share? And if you don't want to share it, I'm not gonna like pull the teeth. You know, I'm seeing lots of head nods, no. Seeing lots of no. Not feeling like sharing it. Okay, cool. Let's do it. Let's do it. And you'll gain confidence as you do this. We might even spend some more time on Wednesday talking about this stuff, because I feel like if we spend the time now to talk about this, the rest is gonna be better. This is foundational. These ideas of this kind of working with this is rough. So proof. First off, we know that any t in T is an upper bound for S. We kind of already talked about that, right? We're still working with those definitions up there. This is for all T and T. So the supremum of S must be less than or equal to T for any T. Why? Looks like, yeah, but why? What are the words? Let's think about what this means. This is the greatest, the least upper bound. What are the words? It's hard, like soup doesn't mean anything, but least upper bound feels like something you can work with. This is I'm claiming that the least upper bound must be less than or equal to anything out of T. And I got this equals to here. Why is that? What is the definition of soup? So first off, soup is an upper bound. So here I'm saying the upper bound, let's write this out in sentences. This is the upper this is n upper bound for S. We know that. We know it's an upper bound because it's literally it is an upper bound. It is the least upper bound. Since this is an upper bound for S and everything in T is bigger than S, these T's can't be less than this, because then, hold on, now I'm starting to confuse myself on it. Yeah, yes, go ahead.
Actually, I have about like the main sort of idea
Yeah.
kind of held me up was, would it be possible for like T and S to overlap at more than one point if you go with like the S is equal to T?
That's a great question. So not more than, they could share one point,
Yeah.
but they can't share more than another. So let's think about why that might be. Let's put them like this. So let's say here's S, and let's say that's 1 to 2, and then.
Oh wait, never mind. Yeah.
You see what I mean?
Yeah.
Yeah, it's good. It's a great question though. If this falls a little bit to the left of that guy,
Yeah.
then there's going to be something shared, and we know that.
That makes more
Yeah,
sense.
yeah. Cool. Yes.
Okay, so I think I can picture that,
Okay, do
but
it.
I can't put it into words.
It's so painful, isn't it?
So, like, we saw when we drew, like, why it's bounded above and below,
Yeah.
that, like, the one point they can share, like, the supremum of S can be the smallest T, but it can't be bigger than that.
That's right.
So, yeah, I don't know how to word.
Yeah. I'm trying. Like right now, I had the words on paper. I'm going to try to not look at them. I'm trying to come up with them again. So let's see here. Why do we believe this statement? So this is an upper bound for S. These are all, everything in T is already an upper bound for S. So since this is a collection, you can think of this is a collection of upper bounds. it's not all the upper bounds necessarily, right? Because we have this picture here. So here, here's S, here's T. We know that everything in T is bigger than or equal to everything in here. So these are all upper bounds. Every single one of them is an upper bound. So the supremum of S, this is the least upper bound. So it lies possibly at the left end of T, possibly to the left of T. These are all upper bounds here. But the sup itself has to live in here. The sup of S must live somewhere in there. So since everything in T is an upper bound, the least upper bound must be less than or equal to any, that's it. The least upper bound must be less than or equal to any upper bound. So this must be true. Let me write that out and see if Camila feels good about that too. So, boy, that sounded really good what I just said there. So every T in T is an upper bound. So the least upper bound must be less than or equal to any other upper bound. I'm not saying that the least upper bound isn't in T, but this must be true. You give me an upper bound on S, it's by definition bigger than or equal to the least of the upper bounds on S. Is that feeling like the right words? Yeah, and you're totally being legit with me when you say that. Yeah, cool. Cormac, how do you feel about that sentence? Liv? Cease? Good, yeah? Chris? Cool, awesome. So once we get this, we're kind of, the proof then, the next step. Talking about this stuff is hard. So now we've got this. We know this. Let's just copy that statement up here. So we know that the supremum of S is less than or equal to T for all elements of T. In the similar argument to this, with the same words, therefore, sup of S is less than or equal to the inf of T. Why? How do I make it from there to there? Corbin.
The infimum of T is greater than or equal to every element of S, is where I started, and then if you're greater than or equal to every element of S for the infimum, and less than or equal to every T for the sup, and then you look at your original inequality of all S are less than or equal to T, you can say then from that the infimum is greater than the sup.
I agree with that. But help me move from this line to this line. So you kind of gave me a fresh proof.
Okay.
That sounded good. How do I move from this line to this line with similar language? So I know that sup of S will work. Sup of S is a what for T? It's a lower bound. So let's actually put this in here. Therefore, sup of S is a lower bound for T. Therefore, sup of S is less than or equal to, so I've got a lower bound for something. So here's sup S, here's T over here. Since this is a lower bound, what is true about any other lower bound if the inf is over here? So here's the inf, so I have the greatest lower bound. What is true about the greatest lower bound compared to any other lower bound?
It's less than or equal to.
It's bigger than or equal to
Oh,
it.
bigger than?
Yeah, because it's the greatest
Oh,
lower
yeah.
bound. Yeah. So if this is a lower bound, then the greatest lower bound must be to the right of this. It's the biggest of all the lower bounds. So let's put this up here and then write that up. Inf of t, because inf is bigger than inf of s, I'm getting sloppy because I'm getting excited, is bigger than or equal to any lower bound of s. That was what I was looking for.
Yeah, that's a lot smoother.
That's again, it's okay. That's okay. What you said was beautiful. It's like a whole proof, though. But do you see? Check out the symmetry in these two arguments. Kind of the same thing. It's appealing directly to the definition of superinf, depending on what we're focused on. And then when you see it, you're like, yeah, that sounds so reasonable. I don't know if I could say it again. But it sounds pretty reasonable. Any other things we want to, let's see, wait. Oh, yeah, can you give me an example? And here's two examples I want right now. I think I kind of already spoiled this. So we've got this here, we've got this thing in the middle. Can you give me an example of an S and a T that have strict inequality and an S and a T where the equality can happen? So now we're going to look for examples of, so next thing here, C, is example of S and T where sup of S is strictly less than the inf of T. And then where sup of S equals T, and I'm going to equals the inf of T. And for this one, I'm going to say an S intersect T is empty. They don't touch. So that'll make it a little bit more interesting. Working through these examples is good. It gives you intuition.
Trying to say like
That one, yeah. So I'm
You
curious,
trying to say-
what are you trying to describe here? Yeah.
like the greatest element is 1 and then it's open to the left.
Yeah, so for this, you need an interval for sure to use those. So what could we pick for the left end? There you go, beautiful, yeah. Love it, that's perfect, now it makes sense, so that's good.
Yeah.
I think that's what you were hanging up on, right? You were
Yeah.
like, I just wrote something, I don't know if it's,
Yeah.
yeah, good.
Yeah, is that is my notation?
Are those closed, both closed?
Yes, I'm just trying to weed out two.
Oh, okay, then put open on both
Okay.
ends. Yeah. And then you just kind of like skipped over to.
Yeah.
Yeah, awesome. But the minute and one could be closed as well.
Yeah,
They
that's
both
true.
can't be closed, that's
Yeah.
the only, yeah?
Yeah, I see.
Awesome. You did that. Felt good.
Thanks though. What, this one?
That's great. Yeah, nice.
Would it just be like maybe like this?
Perfect.
Just cause the others don't.
I got it. They kind of like kiss, but they don't.
Mhm.
Yeah. Someone I haven't chatted with, because I know the people I've already chatted with have this going. So,
For that one, I did S equals the closed interval of 0 to 3,
cool.
and then T equals the closed interval of 5 to 6.
Love it. Sounds good. Just way far apart, right? There's a space between them. Yeah, beautiful. I also saw a couple people doing discrete sets. So, discrete sets. I think, so who did some discrete sets like? Could do that. All good too. Yeah. Someone else, Chris sees. You may got me in the equals thing here.
For that, I did S is equal to the interval that contains 1 and goes up to 3, but doesn't contain 3.
Cool. So contains 1, like that, and then goes up to 3, open.
Yep.
Okay.
And then I guess for T it'd be like open at 3 and then goes up to 6 and contains 6.
Very nice. Yeah. So essentially, it's 1 to 3. Skip 3, going up to 6. Very nice. Yeah. You see that? So the soup and the imp are equal when these two sets. I like the kiss. They're like kissing. They're just like touch. They're not touching, but they're as close as they could get without touching. I could, as I was talking to Cormac, we could even make them kiss a little harder by doing that, and it still works. So this one has 3 in it, this one doesn't. Inf of this is 3, soup of this is 3. So this is maybe even closer, whatever that could possibly be. It's actually not closer. Does this sound good? We feel a little better about soup and inf? Awesome, cool. Let's finish up a few things. I just wanted to do that little work session there. Because I want to talk about a couple major results, one of which is on the quiz, but let's talk about the completeness axiom. Completeness axiom, Archimedian Principle, and then denseness of Q in R. So the completeness axiom, that sounds pretty fancy. And it's an axiom. So it's kind of an assumed thing in a way. So axioms are fundamental principles that we work from, and in general they're things that don't necessarily have a justification. Right, they're kind of like there is, but it's probably a tone, like about a mile thick, the justification for it. So the completeness axiom, does anybody remember what it is from your reading?
I think it basically said that for any set like S in the real numbers that is bounded above has a real number supremum.
Exactly. So where S is bounded above, sup of S exists and is finite. And is finite. Let's put that here. Yeah. You can find the supremum of any bounded thing. A contrasting one would be if I was bounded below, I have an infimum. Now, you might think, well, this seems kind of obvious. It seems kind of like, duh, we've been almost doing it. We've been kind of almost assuming it. But it's only because R is so complete. So let's focus on Q. What if all we had were the rationals? What if we were the Greeks? And we were like, no way, everything is a fraction, right? That was their fundamental thing. The square root of 2 was very upsetting. So what if every number we had was rational? Now, I'm about to write something that's irrational, so it's a little weird. Consider the set S equals set of all Q in Q such that Q is less than the square root of 2. What's an upper bound? Square root of 2 seems like an upper bound. We can't get there. So square root of 2 is an upper bound. What if someone was like, I don't like the square root of 2. What can we give them? Just an upper bound.
4.
Nice. So is 4. So don't freak out. 4 is an upper bound. So this thing is bounded above. So this S is bounded above. And it's certainly bounded above by rationals. Yeah, lots of them. Lots of, in fact, any integer from 2 on up will work. But when I'm thinking about the least upper bound, let's draw this set out. So here's the reals, and here's square root of 2, and that's not in my set. And my set S, I don't want to draw a solid line over here, because actually all I'm doing is thinking about the rationals in there. And then so here's some weird number that we don't know about, and it's called skirt. We don't know what that number is. But we know it's not rational. We know that much. So what is the least upper bound here? Well, the least upper bound, what is the least upper bound if I allow all rationals? It's square root of 2. So in R, if we allow all the numbers, the sup of this set equals the square root of 2, but that's not a rational. But square root of 2 is not rational. There is no rational least upper bound on this set. So there is no rational least upper bound on this set. How do I know that? What could I say? Cormac, yeah.
I guess any number that you said was a rational least upper bound, you could just take a half step closer to square root of 2 or something, and it would still be a rational number.
You can just keep getting closer and closer to it. Yeah, absolutely. And if I were to say, well, there's a number to the left of square root of 2, there's a lesser upper bound that's rational, then you could just use your argument. No, I can move a little bit to the right. There's actually a number in this set to the right of it. So if I fall over here by any amount, there's something in there. If I fall over here by any amount, so I pick some rational over here, all I gotta do is, no, I can get lesser. I can move closer with another rational. So that averaging, that's a great way to think about things. So case in point is that Q is not complete. That's kind of what the irrationals give us. Filling in all the holes. So this completeness property does not exist for everything that you can think of. Let's talk about Archimedean property, denseness, and I think I can bring this home before we leave here. Do me a favor. Between now and Wednesday, start on your homework for Friday. All right, let's start on that so that when we come in on Wednesday, we can talk about it, have meaningful conversations, because you'll have suffered. You will suffer. If you have not suffered on this homework, you're probably doing it wrong, or you haven't done it. So if you're not feeling angst when you look at it, not angst, but ugh, what? Look at it again, or look at it for the first time. So let's take a look at the Archimedean property. I don't know enough about Greek philosophers, especially Archimedes, to know exactly what it was that, why this is named the Archimedean property. I just know that it is. So if we have two real numbers, A and B, and we'll say that B is greater than A, and they're both positive. So in other words, B lives to the right of A. That's all I'm saying. And here's 0. Something like that. Draw pictures. Draw pictures. Pictures can really screw you up. But man, they can also give you something to hold on to in the weirdness of all of this. Then there exists a natural number n such that n times b minus a is bigger than 1. Let's think about this. That's a weird thing. Let's make some sense of it by thinking of some examples. So for example, if b is 1/2 and a is 1/3, here's 1 over here. So these two numbers sit like this. The Archimedean property says that the distance between them, I can find some multiple of it, some whole multiple of it that's more than 1. So here, first off, b minus a is a 1/6. Half minus a third is a 1/6. I know fractions are maybe not things you think about a lot. But you'll believe me, and you could easily convince yourself of that. So I'm looking for an n times 1/6 that's greater than 1. What n's would work? 7. Yeah. So n equals 7 works. Let's put a little question mark there. Everybody see that? So no matter how close these two numbers are, I can always find some whole number that's bigger than them. I want to write a consequence of this that really is the heart of it, that is going to help us more. i.e., there exists this n such that the distance between these two is less than 1 over n. Notice I can divide both sides by n. Besides this proof we're going to do about the denseness of Q in the reals, besides that, this is probably the most useful form that we'll ever have. And notice that this is a positive number because b is bigger than a. So one way I could say this is, given n any positive number. Oh, let's just introduce one of our best friends, epsilon. So in other words, epsilon is greater than 0. You're going to be so epsiloned out by the end of the semester. There exists a natural number n such that epsilon is less, 1 over n is less than epsilon. Did I?
Yeah, I think you flipped the
I flipped the freaking inequality, thank you. 1 over, yes, thank you. Yeah, that wasn't making sense here, sorry. I divided both sides by n, that's a positive number, it doesn't change the inequality. Yes, thank you. And I'm sure things feel so nebulous that you're like not even sure. You're like, oh, it doesn't seem right, but I don't know, everything else is weird. So such that epsilon is 1 over n is less than epsilon. I can always find this 1 over a whole number that's less than any number you give me. And here, like, how do you apply the Archimedean property to this? Just say epsilon is your b and 0 is your a, so that b minus a is this epsilon right here. All right, we gotta end this because your brains are probably, how about this? How about we don't do the next thing? We will do it on Wednesday. So you're gonna start your homework, and what I want you to do is look at the proof of the it's 4-7, it's on page 24, the denseness of Q. So just look at that, and we'll talk about that on Wednesday, but I can see that your brains have about reached capacity on this stuff. Check out that proof. We'll go through it at the beginning of the hour. It'll be better if you just look at it anyway first. How you doing, my friend?
Is that the denseness of Q?
That is not. The denseness of Q says this. It's close. It's close. Denseness of Q says you give me any two real numbers, there's a Q, there's a rational between them. This is a little different. This is saying no matter how small a positive number you give me, I can find a multiple, I can find a 1 over n that lies to the left of it. See, this gives me like numbers like that. So if I said epsilon is 1 over pi, that's horrible. But I can find a nice 1 over n thing that's less than it.
Yeah. Aren't those like sort of like for the one on the left, if you were to move like the a over to 0, like isn't that kind of saying the same thing?
Yes, and the proof goes very much like that, yes. Yes. But I think keeping this version a little separate from it will be good. You're right, you're actually right. I think we could come up with a proof that would, yeah. I like that. Cool, yeah, good observation. Awesome, thanks everybody. See you on Wednesday.